Paul sir. So I'm going ahead with the presentation here on our topic additive manufacturing, reinventing design and manufacturing. So the the content I will be discussing today are the following: like definition of additive manufacturing. Additive manufacturing is a natural process. Then the comparison with other manufacturing processes, evolution of additive manufacturing as a manufacturing process, the need for additive manufacturing, the advantages and limitations, the classification, the need for DFAM, design for additive manufacturing, various applications of AM from the Indian scenario as well as the global scenario, additive manufacturing and industry 4.0, the challenges and opportunities of additive manufacturing, the recent research works at RRCAT, and the summary of the work. So how we make parts conventionally? So either we have a formatting manufacturing where we go for deformation, we change the shape of the block and bring out a component out of it, or you do casting, you join different pieces of materials metals and then bring a component out of it, or subtractive manufacturing where we try to remove the material from a component and try to make an actual requirement as per the requirement. On in some cases we do a combination of all any of these two processes, and like a subtractive or deformation followed by a subtractive manufacturing, or like that we have multiple processes that is used for making a component, and that is called hybrid manufacturing. So these are the way we make the component conventionally. And when we go in 1987, the minus sign has changed to plus sign, and a CNC machine which removed the material from a component is used for adding the material. So the minus sign became a plus sign in the year 1987, and the additive manufacturing was introduced to industries. So what is the definition of additive manufacturing? As per ISO or ASTM 52900, additive manufacturing is a process of joining materials to make parts from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing and formative manufacturing methodologies. So with this definition, we can find out 5 criteria for qualification. Or we could say that a process should qualify all these 5 criteria to be called as additive manufacturing technology. So first is a process of joining of material. It should be a process of joining of material. It should start from 3D model data, whether it can be a CAD model data or from a reverse engineering data, or output of a numerical analysis. It should start from a 3D model data. And it should be a layer by layer build up approach. Means the component should be built in a layer by layer fashion. And it should not be a subtractive manufacturing, and it should not be a formative manufacturing. So these are the different criteria for calling a process as additive manufacturing. If you come to the synonyms, there are different ways in which additive manufacturing has been known in the world, like 3D printing, rapid prototyping, additive fabrication, layer manufacturing, rapid prototyping. There are different ways in which people call additive manufacturing. And now ASTM and ISO standardized additive manufacturing as a technology as a single terminology for calling these processes. And if we consider additive manufacturing, it is a natural process. And if you can consider it as a natural process, then it can be compared with a plant growth. You can see how a plant grows from a seed to a plant, because it adds material and become a plant. Similarly, if an infant becomes a man, it's also an additive process. And if you see the construction work, it also happens in a layer by layer fashion, in which the bricks are arranged in a layer by layer fashion to make a building. So additive manufacturing existed for a long time, and recently it was taken to manufacturing because we got the technology. Initially we didn't have the technology to tame it, and we didn't have the technology to bring it to the manufacturing sector for industrial production. But now we have the technology to bring it to industries, and now we are using it for manufacturing of engineering components. So when we compare additive manufacturing with other manufacturing processes that are formative and subtractive, we can say in terms of methodology, additive manufacturing means we are adding the material, while in subtractive we are removing the material, or in formative we are shaping the material. Coming to the lead time, it is less in additive and it is high in subtractive and formative. Coming to the surface finish and dimensional accuracy, additive manufacturing is low to medium, while and subtractive is medium to high, and formative is medium. Like if you say material, additive manufacturing ideally doesn't have a material limitation. We should develop the process, we should develop the technology processing any materials. But in subtractive and formative, we have material limitation. In subtractive, mainly it is limited by the hardness of the material, and formative also it is limited to metals and plastics. Size of the components in additive is mainly limited to the machine sizes, while in subtractive we can make large components. In formative also we can do it. Complex geometry, it is a major advantage of additive manufacturing. We can make complex components. We can bring components of very high complexity as compared to other manufacturing techniques. And coming to the last point, the green technology, additive manufacturing, since we add the material in a layer by layer fashion, there is no wastage of the material. We can say that almost 60 to 90% of the material in minimum, like you can say that we have, you can have a good amount of material usage, and the minimal material wastage is there in additive manufacturing as compared to other processes where we are removing the material. So these are the ways in which additive manufacturing can be compared with other other conventional processes for manufacturing the parts. And one more important thing is the buy to fly ratio. Buy to fly ratio is an important point in the aerospace sector, where they consider the low buy to fly ratio as an economical part. Buy to fly ratio is nothing but the ratio between the amount of material purchased and the amount to the amount of material that is converted, or the amount of the mass of the product. So if you have a 10 kg of material purchased, and usually in subtractive manufacturing, we have only 1 kg that is converted to the actual product. That is a buy to fly ratio is typically 10 in for subtractive manufacturing. But in case of additive manufacturing, we can have a buy to fly ratio close to 2, and sometimes we can bring it close to 1 also. Means there is no material wastage. We are only adding the material as per the requirement. And this is one of the reasons why additive manufacturing is seeing a lot of applications in the aerospace sector. So now we have a poll here. I request all the participants to do the poll. We'll be giving 30 to 40 seconds for that. Okay. Yeah, additive manufacturing, which among the process, not a mandatory condition for a process to qualify as additive manufacturing as per ISO ASTM 52900. Yes. The answer is shapeless materials are needed, because we need a process that is required for joining of materials. We need a process. It's a process of 3D that starts from 3D data, and it's a layer by layer build up approach. As per the ASO ASTM, it's not a process that requires shapeless material as per the ASTM standards. So now the evolution of additive manufacturing as a manufacturing process. So initially in 1987, the process started with stereolithography, and 1991 the next process, that is fused deposition modeling, came up. In 1992 the next process, cell-T laser sintering. Like that, the process evolved, and in 2000 we had the first multicolor AM system, and 2002 we had the electron beam based additive manufacturing system. Like that, the technology evolved from 1987 to the present date. And we can see also that initially the application of the technology was mainly in rapid prototyping, rapid casting, rapid tooling, where they used the technology for making molds and dies for other conventional manufacturing process, or supporting other conventional manufacturing processes. Then the application extended to the automotive applications. Then metal AM came into the picture. Polymer additive manufacturing is started using for medical applications. Then medical implants came into the picture. Like that, people started going into different dimensions of additive manufacturing, and now we are into the nano manufacturing sector. We are into the biomedical implants, and we can now, it is predicted that by 2032 we can print full body organs using additive manufacturing. So it's a way the technology is growing. So if you see, why do we need additive manufacturing? Because there is a cutthroat competition that is happening in the industries, because there are more number of players and more models available, and there is requirement of reduced volume per product. And another thing is the adverse duty conditions. All the industries are going to adverse duty conditions, or for improving the efficiency, because people are going to adverse duty conditions. Means we are trying to increase the operating temperature in the industries, the adverse high pressure conditions, high temperature conditions, like that is known as extreme duty conditions. So these applications requires high performance components. And the another thing is the fast changing technology, because there is 65% success rate for new product with superior technology. So all these things brings to the fact that additive manufacturing is required for improving the current manufacturing scenario, and for using the for satisfying the customer requirements. And if you see, in an industry, The number of variants are increasing with time, and the product lifetime is reducing with time. And at the same time, the product complexity is increasing with time, and the required delivery time is also reducing. So what we can conclude here is that the requirement is an immediate delivery of best quality product with maximum features at lowest price. So that's the major reason why additive manufacturing is required in the industrial manufacturing sector. Another way we can explain the need of additive manufacturing is this flowchart. In industries, if you want to bring a component, we have three different stages. One is design, a production, and application. Initially, we have a design concept, that is not a synthesis stage, where we have a design idea. Then it is analyzed using different tools. Then it is documented and drawing is done. In the production stage, we have a planning, where we do the production planning. Then we go to once the design is finalized and planning is done, we go for the raw material procurement. Then the tool procurement will be done. Then the manufacturing program will be developed. Then in the application stage, we have quality control, packing, and the final deployment or usage. But it comes to additive manufacturing, we can see that these number of stages can be eliminated. Documentation and drawing is not required because we have a direct 3D model that is to be used. We have a 3D model developed in the synthesis stage, which is analyzed using FEA tools or various tools in the analysis stage, and which can be directly used for the programming or the manufacturing part. And there is no need of production planning. There is no need of raw material procurement, because in additive manufacturing, we use shapeless materials. We use wires or powders of the material, and these material can be procured earlier before when the application is finalized for the particular component. And in conventional manufacturing, since we have to wait till the final design is freeze for purchasing the raw material, it is a problem in conventional manufacturing because it delays the production process. Again, tool procurement is not required in additive manufacturing because our tool is a laser or electron beam or whatever jetting head we use in additive manufacturing. So tool procurement is also not important in additive manufacturing. Like that, we can have different stages that can be eliminated when we use additive manufacturing in industry, and thus which leads to reduction in the time, as well as it leads to cost savings. So I would like to explain the different advantages of additive manufacturing here. So first is complexity for free. So this is one of the typical term that is being used in the industry when you use additive manufacturing. That is, complexity is for free. Means if the complexity of a component or the design complexity of a component increases, the unit cost doesn't increase in additive manufacturing. It is mainly because in additive manufacturing, you convert a complex 3D model into its simple 2D sketches in each and every layer. So every 3D component or every complex design just converted into a simple 2D cross section, which can be a line or a circle or anything like that. A 2D sketch is obtained. So thus, the complexity doesn't determine the cost of the component like conventional manufacturing. While in conventional manufacturing, the cost depends on the complexity. As the complexity increases, the cost of the production also increases. So that is why in additive manufacturing, we have complexity for free. Simplicity of part fixturing, because additive manufacturing is a contactless process. There is no direct interaction between the tool and the component like subtractive manufacturing. So there is simplification of part fixturing in additive manufacturing. So then we have mass customization. Additive manufacturing combines the two extremes of manufacturing, that is mass manufacturing as well as customized manufacturing. Mass manufacturing means you are producing components in a bulk, in a large quantity, while customization means you are bringing the component as per the requirement of the customer. So additive manufacturing is having that salient feature of combining all these. One of the example you can say is the fabrication of dental implants using additive manufacturing, in which we can have a single bill plate. You can make number of dental implants of different designs. So at the same time, you are doing mass manufacturing and you are doing customized manufacturing also. Another is this integrated components. Now it's an era of smart components where we can integrate sensors during the manufacturing onto the component, and which can directly control the process. So integrated components, these are directly used by NASA for controlling the process. Like they integrate sensors using sheet lamination additive manufacturing process to measure the temperature and pressure during the process, so that they can control the process online. Material design freedom. So additive manufacturing allows you to add the required material at required locations. Since we are doing layer by layer manufacturing, so we can add the material at the location that we require. So it can, as we can see in this image, you can have a stainless steel at one part and copper at the another part. So you can have multi materials in a single component, and thus it gives the freedom for you to go for high performance components by joining these dissimilar materials. So another advantage is the logistics freedom, because here we have additive manufacturing allows you to design a part in one part of the globe and you can get it printed at the other part of the globe, and you can do the designing, you can do the analysis online. So it allows you to give a logistics freedom also. And the final one is the minimal material wastage. As I mentioned earlier, additive manufacturing builds a material in a layer by layer fashion. So there is no material wastage. We are only selectively adding the material as per the requirement, as per the design needs. Coming to the limitations of the technology, if you have, the first thing is the high production cost, because the machines are really costly. And initially the machines were costly, I can say, but nowadays as the patents are getting expired, the machines are getting relatively cheaper. But anyway, high production cost is one of the limitations of the technology. Another part is the mechanical properties, because we have anisotropic mechanical properties in the additive manufactured components, and the mechanical properties tend to be different from the conventionally built components, which are generally used as standards for any application. So this difference in mechanical properties from conventionally built parts offers a challenge for the industries to use the technology. Requires post processing, means as I mentioned earlier, additive manufacturing, the surface finish is low, the dimensional accuracy is also low to medium. So we require post processing treatments like machining or heat treatment to improve the properties. Like that, there are requirements of post processing treatment after the manufacturing to improve the quality of the build components. Limited build volume, because the size, maximum the size of the components that can be built in additive manufacturing is dependent on the machine build volume. So limited build volume is another limitation of the technology. Then stair stepping effect, you have components built in a layer by layer fashion, so you have a stair stepping effect, as we can see in the image. So this is also known as Christmas tree effect in the industries. So as I can mention here that the additive manufacturing methodology can be of three stages. One is pre-processing, processing, and post-processing. In the pre-processing, as I mentioned earlier, we have a 3D model. So we have a computer design model, or a 3D scanning data, or a numerical analysis data, or a 3D model that is generated from various sources. Then it is sliced into different layers. So these slice and the parameters are set in the machine. So once the slices are generated for a particular component, if you say, take the example of a hollow cylinder. If you take the example of hollow cylinder, we have number of slices of circles. So we have a 3D model of a hollow cylinder which is sliced into different layers that are then circles. Then these number of layers are fed into the machine in the processing stage. In the processing stage, we feed the machine settings, we feed the machine parameters depending on the additive manufacturing process, and the material is added in a layer by layer fashion and happens in the processing stage. So we get the component by adding the material in the processing stage. Finally, after the processing, we go to the post-processing stage. As I mentioned earlier, we need post-processing for additive manufactured components. So it can be machining, it can be heat treatment, it can be support structure removal, or painting. Like that, we need post-processing techniques also. So at the end, after processing, we go to the post-processing stage where we did all these treatments to tailor the properties of the component as per the requirement of the customer. Then we get the final product from the additive manufacturing machine. So these are the different stages in which additive manufacturing takes place. Coming to the classification of additive manufacturing, as per ASTM, additive manufacturing is classified into 7 different processes. One is powder bed fusion, vat photopolymerization, material extrusion, material jetting, binder jetting, directed energy deposition, sheet lamination. So these are the 7 technologies in which additive manufacturing is classified by ASTM. The first process is vat photopolymerization. Here we can see that it's a process in which liquid photopolymer in a vat is selectively cured by light activated polymerization. So in this we have a vat in which we take the photopolymer solution or the liquid, and in which so we take the liquid here, and then the laser comes and selectively cures the region as per the requirement. As I mentioned earlier, if I take the example of a hollow cylinder, the laser selectively cures the region of a circle. So then the build plate moves down, the next layer of liquid will be spread on the surface, then the laser selectively cures the region as per the requirement. Like that, the 3D component is built in a layer by layer fashion. The major advantage of this technology is the higher accuracy. It can be used for micro manufacturing application. Can have multi materials also. And the major limitations of the technology is the material limitations, and the cost is relatively higher as compared to the other polymer based technologies, and it finds application in medical, in tooling sectors, as well as in microfluidics also. Then comes the material jetting process. Material jetting process is an additive manufacturing process in which the droplets of build material is selectively deposited on a build platform. So we have we can see that we have a printing head here, and we have a separate head for support material as well as build material, and the material is selectively deposited on a substrate as per the requirement. Like if you take the same example again, if you take a hollow cylinder, I will have a cylindrical layer to be deposited, and the material is added selectively in a circular fashion as per the requirement. And once the deposition is done, the UV curing will be done using the laser. So this is a process. It's also similar to vat photopolymerization, where we have a vat and the laser is curing the liquid, while here we have a deposition and followed by a curing process. And this process also having higher accuracy, surface finish is very high, but similar to the vat photopolymerization, we have a higher cost here, and the material limitations are also there because it should be photopolymerization is the major mechanism here. And applications are generally seen in automotive, medical, jewelry, and electronic sector. Coming to the next process, our material extrusion process, which is most commonly known as fused deposition modeling or fused filament fabrication. In this, the material is selectively dispensed through a nozzle or an orifice. So it's an additive manufacturing process in which the material is selectively dispensed through an orifice or a nozzle. So we can see from here that we have a head here, and we have material coming from spools. We have one or two materials, multiple material can be used, or a single material can be used, and it comes to the head, and here it is getting heated, and material is getting deposited onto a substrate. So then build plate, the material get deposited on the build plate, then the layer by layer deposition happens as per the as said initially, then the component is built in a layer by layer fashion. So the major advantages of the technology is the wide acceptance of the technology, because it's low cost, it is simple and easily available, and it's most commonly used in the industries as well as in the education sector. But the disadvantage of technology are the lower surface finish or the lower accuracy, and also the low anisotropy in the mechanical properties. It is seen in various applications in terms of concept modeling, rapid prototyping. Sort of lot of applications are seen for this particular technology. Then the next one is the sheet lamination. Sheet lamination is an additive manufacturing process in which the sheet of materials are bonded to form a part. Means we have sheets of materials added one over the other, and it is joined by using some mechanism. Can be using adhesive, it can be using ultrasonic welding technique, but one major criteria here is that there is no melting, then there is no solidification. So there is no heat source used in this particular process, and the sheets are joined by using adhesives or ultrasonic, or in the solid state welding techniques. Basically they are used for joining the sheets. So the advantage here is that there is no thermal stresses involved in this as compared to other metal additive manufacturing processes, which will be discussed later on. And we can have multiple materials also, because we have different, we are adding sheets in a layer by layer fashion, so we can have multiple materials in different sheets. There is no support materials that is required, because we are adding the material, and there is a support there is a sheet below the surface which can be used taken as a support material. The disadvantage is the resolution, lower resolution, because we are using sheet material, and the resolution in the z-axis depends on the thickness of the sheet. So it's one of the limitation of the technology. Then the next process is the binder jetting process. In binder jetting process, we have a powder layer that is spread on the surface, and a binder is used for joining this powder material and forming a component. So it is defined as a process in which liquid bonding agent is selectively deposited to join the powder material. So we can see that, as I mentioned earlier, we have if we want to make a circular part, we spread the powder on surface, and the binder selectively joins the powder particles in a circular fashion, so that we can get a particular layer. Then the layer by layer buildup continues, and we get the final component out of it. So this process, the advantage of this process are we can have multi-color components, multi-material components, etc. So this process, and there is one more advantage, is that since we have a powder layer beneath the surface, like you can see here, there is no need of support structures. We can make any overhang component here without any support structures, because the powder layer below can support these overhangs. And this component binder jetting can also be used for variety of materials. It can be used for polymers, it can be used for metals, it can be used for ceramics. But for metals and ceramics, we use it in an indirect way. It's called indirect additive manufacturing. The next process is the powder bed fusion. Powder bed fusion is a process in which the thermal energy is used for selectively, the focused thermal energy is used for selectively fusing regions of a powder bed. So we have a region of powder that is spread on the surface. Then the laser comes and selectively melts a region as per the requirements. So as I mentioned earlier, if you want to make a circle, the powder is spread on the surface, then the laser selectively melts the region, the circular shape, and then we get a circular layer. Then we build the circles one over the other and we get a hollow cylinder. So this is the way powder bed fusion works, and it's the most commonly used metal additive manufacturing process, mainly because of its ability to build highly complex engineering components, because it can build components in a layer by layer fashion, and since the powder layer is below the surface, it can build components with very high overhang angles also. So it can be used for building very complex components. The another metal additive manufacturing, the last one, is a directed energy deposition, where we use a focused thermal energy for melting the material as they are being deposited. Means we use a energy source, which can be a laser or electron beam or an arc. While in powder bed fusion, I forgot to say one thing. In powder bed fusion, we use laser and electron beam as energy source, while arc is not used an energy source so far. While in direct energy deposition, we can use laser, electron beam, as well as arc as an energy source, and we use energy source from here, and we feed the material, which can be wire or a powder, and it gets melted and deposited on top of the surface, and we get a deposition. And it can be considered as a pen, and as we move the pen, as we move it over the surface, we can create the part as per the required 3D geometry. Since powder bed fusion and direct energy deposition are the more commonly used metal additive manufacturing process, I would like to explain them a bit more. So you can see from this videos that how the process happens. In direct energy deposition, we have a deposition that is happening in the layer by layer fashion as per the by feeding the material online. While in powder bed fusion, we can say the powder is spread out the surface, then the laser selectively comes and melts the region as per the requirement. Then if we compare both the processes, we can see that there are relatively higher complex components can be built in powder bed fusion, and part size is unlimited. We can go for a larger size components in direct energy deposition as compared to powder bed fusion. Coming to dimensional tolerance, it is in micron scale in powder bed fusion, while DED it is normally in the scale. Layer thickness is typically in the range of micron in DED, and in powder bed fusion, the micron scale, and in DED it is in the scale. And the cost of the powder used in powder bed fusion is relatively higher as compared to direct energy deposition. And direct energy deposition can be used for repairing and remanufacturing applications, while powder bed fusion is having limited application in that. And coming to multi-material components, as I mentioned earlier, we can have multi-material component in a single part, or we can join dissimilar materials also. So this is more commonly used in direct energy deposition, while there is literature that shows the application of powder bed fusion also, but the application is the flexibility is relatively lower as compared to directed energy deposition. So now we have a poll here, and I request all the participants to kindly participate in it. So yeah, the answer is VAT photopolymerization. The which among the following process use liquid as the raw material? So in VAT photopolymerization, as I mentioned earlier, we have a VAT in which we take the liquid photopolymer and we do in a layer by layer fashion. So this VAT photopolymerization is a process or where we use liquid as a raw material. So the next poll is here, and please answer this. So, which among the following is not used as an energy source in powder bed fusion? Yes, the answer is arc, because laser and electron beam are the most commonly used energy sources in powder bed fusion process. Now we are going to the next stage of our talk where we discuss about design for additive manufacturing. So initially we had there are two ways in which product engineering, that there are two major concepts in product engineering. One is functionality, another is manufacturability. There is no need of building a component which cannot function, and there is no need of designing a component which cannot be manufactured. So brought out the concept of design for manufacturing. Then with the when advancements in technology, with the advancements in mass manufacturing, design for assembly came into the picture. So thus design for manufacturing and assembly came into the industrial scenario, and it involves majorly design concept is initially made, which is going to the design for assembly, where we design the component for the assembly requirements, where we go for the minimal fastening, minimal assembly requirements. Then after that we go to the design for manufacturing stage, where we pick the design which can be manufactured also. So this is a combined approach of design for manufacturing as well as design for assembly, and it is being used in the industry for a quite a long time. So with the major problem with this is that the conventional manufacturing which uses this concept cannot give us the complete design freedom. So with the additive manufacturing we can go for complex components and we can have a higher design freedom. So with this, the concept of design for additive manufacturing came into the picture, and we can see that there are basically three methodologies for design for additive manufacturing. One, the direct part replacement, other one is adapt for am, and the other one is a design for am. In direct part replacement we are only changing the manufacturing process, means we are changing the additive manufacturing process, the conventional process with an additive manufacturing process. In adapt for am we change the form and process. In design for am we change the function, fit, form and process. So all these are changed during this design for am concept, and these three methodologies can be compared as crawl, walk and run for companies to use design for am or for using additive manufacturing. So these are the different stages and different ways a company can bring additive manufacturing into their manufacturing sector. So first we will discuss one by one. Direct part replacement is one in which, as I mentioned earlier, only the manufacturing process change, means we change the manufacturing process from conventional, that is a subtractive manufacturing or a formatting manufacturing, to additive manufacturing. It is one of the examples is a reverse engineering, where we only change the manufacturing concept. We take the component, we do the scanning of that, get the 3D model from it, then we convert it to a 3D model and then fabricate using additive manufacturing. Fabrication of spare parts is another example. Adapt for am means we are changing the form as well as the process. Means one two examples I can cite is removing the complexity from the process. Means if there are two multiple processes that has to be used, like a combination of two manufacturing process that has to be used, we can change it and we can build it using only additive manufacturing. Reduction in number of parts means we are combining the parts and we are reducing the assembly by additive manufacturing. Design for additive manufacturing is the final stage for an industry, where we change the form, fit, function and process, and we have the designer has the complete freedom to redesign the component from scratch. So this transformed design for manufacturing to feature based design and manufacturing. So these are different ways we can do. Is one is hollowing and porous components, where we can reduce the weight of the parts. Topology optimization also, it's an FEA technique where we reduce the weight of the component as per the loading requirements, as per the design requirements. Then increase heat transfer, we can have conformal cooling channels, we can have fins attached. So there are different ways of increasing the heat transfer. Mass customization, as I mentioned earlier, one of the examples is the dental implants, where we can have a large number of components of different designs, then build the component as a single unit. The one of the common example is the GE fuel nozzle, where we could combine lot of the GE could combine lot of components, lot of parts. We can reduce the number of parts by using additive manufacturing. So one of the examples where a topology optimization is applied to a bracket, where we have an original design which is optimized as per the loading condition, and we could achieve a weight reduction of around 18%. So now I would like to explain with a case study which we got from Renisha, and one of the manufacturers of the powder bed fusion technology, where they got it combined with transformers, and they tried to build a front suspension system. So the conventional system is made of 12 components, and they are joined by using joining techniques. They are made of stainless steel, so density is very high, the weight is very high. So they wanted to reduce the weight, so they used topology optimization techniques, and they could make a new design which is highly complex. So they could bring it using additive manufacturing. They manufacture the component by using titanium, and the weight reduction happens to be around 40 percentage. And so with this they could reduce the weight of the component by 40% by retaining the same rigidity and strength. So this is one of the typical examples that is seen in the automotive sector, where we can reduce the weight of the component, at the same time we can retain the strength of the component, which helps us to improve the fuel efficiency, or we can retain the fuel efficiency also. So now there's a poll. I request all the participants to please attend this. So adapt for AM additive manufacturing involves changing both form and process. The answer is correct. So we can change both the form and process for adapt for AM, instead of direct replacement where we change only the process, and in adapt for AM we can replace form as well as the process. Now the next part of the talk is on the applications of the technology. So additive manufacturing, as I mentioned, is used in several sectors, so we would like to cover some of the sectors in which additive manufacturing is used, and I will go a little quick in this section considering the time limitations. So additive manufacturing, one of the application is seen in the aerospace sector, where the major advantages is on the complex geometry, customized parts, high performance components are required, because in aerospace we have to work on high extreme duty conditions, so they require super alloys or many advanced materials, so they are difficult to machine, low buy to fly ratio. These are the different requirements in aerospace sector. So considering all these requirements, additive manufacturing is one of the leading technology that is to be used in the aerospace sector. One of the case study that we got is from the Vikram Sarabhai Space Center in India, the national lab under ISRO. So in Trivandrum, so they developed a lot of components of brackets, gas charging manifold, brackets, fit end fittings, and fuel injection strut using different materials like titanium and Inconel 718, using laser powder bed fusion. And they had a thorough investigation on the mechanical properties and the characteristics of the build components, and they could, and now the functional testing is in progress, and sooner they will be integrating some of these components into the actual application. And we can also see we also got an information from them that they are also going to build large size components using DED based additive manufacturing. So in the Indian sector, the Indian Space Research Organization is coming in a bigger way in the area of additive manufacturing. This is one of the case study that we got from Siaki, the manufacturer of electron beam based directed energy deposition technique, and they build titanium propellant tanks for the space systems, and the size of the tank is 46-inch, and it has three parts. One is a one cylindrical part and two domes which serve as the caps. So the major advantage is with this the deployment of the additive manufacturing or the electron beam DED for this particular application is the 80% material savings. Normally they have to buy a large block of titanium and they have to machine it completely, means that there is a lot of material waste that is going to happen for making this sort of tank structure. So with this technology they could reduce the material wastage, and they could reduce the lead time also, and they could reduce the cost. So this is another example. In case in defense sector, we can say that this is the same case study, another case study that is we obtained from Siaki, where they used electron beam DED technique for building titanium ballast tank, where they in typical generally they use the forging techniques for building these tanks, but the lead time typically in the conventional manufacturing is around 16 weeks, and they could reduce this lead time to around 8 weeks. That means a significant reduction in terms of lead time is obtained, and the cost also got reduced. So this is one of the application of DED in the defense sector. And coming to the biomedical sector, where additive manufacturing is being used for a long period of time now and being used for various number of applications. The major advantage of additive manufacturing that attracts its deployment in the biomedical sector are the anatomy and patient specific solutions, because every person is different and every person's requirement is different. So we need implants for a particular person and the requirement changes with the person. So additive manufacturing can bring patient specific solutions by using a typical path flow that we see in additive manufacturing. You can see from here that if a person meets an accident, we can have a CT image of the person and we can convert to 3D model. Then we can do the fabrication and transportation can be done in a very quick time period. So we can bring patient specific solution using additive manufacturing. Pre-surgical planning can be done, which helps the surgeons to plan the surgery before the operation, actual operation. Study of the parts after their treatment is done, like the 3D printing or additive manufacturing can be used for analyzing the patient condition after the recovery, improving patient education. The doctors can use the technology for explaining the condition or the criticalities to the patient. Then bioprinting is another way of using additive manufacturing. We can use human parts by using additive manufacturing. One of the example that we got is from NIT Warangal, where their additive manufacturing team used the technology for helping an 8-year-old girl from Hyderabad, because this girl had a mandible and maxilla joint, so she was not able to chew. So they developed they used the CT scan to develop the 3D model, then build the component which helped the surgeons to visualize it, then go for the surgery. And they with this technology, with the deployment of the technology, the girl is now recovered, and we can see from here the before and after condition, before the surgery and after surgery. So this is one of the examples regarding the applications of additive manufacturing in the biomedical sectors. So another application that we took is from Imaginarium India, one of the additive manufacturing companies in Mumbai. So they use additive manufacturing technology for building customized jewelry. So what they do is they use the material jetting technique to make molds, and so that they can build it with high accuracy. And this mold is used for making the cast using the gold jewelry components. So this is having a very lightweight and very complex design. So this is one of the application of additive manufacturing in the jewelry sector. So next, the construction sector. This is one of the case study that we took from NTU, where they used additive manufacturing for building for the construction application. This is one of the toilet that is built using additive manufacturing in NTU Singapore, where they use a material, cement-based material, which has 70% of the industrial byproducts, which is such as fly ash, and they could build 1.8 meter height structure in 3 hours. So then they arrange manually the door and the everything, and they could make the toilet in a very small time period. So there is one more case study that coming from India is that we have a two-story building that is built in Chennai by L&T. That is another case study that is coming up, and there is a team that is working in IIT Guwahati, working in the area of 3D printing for construction applications. So that is the Indian scenario where people work on construction applications for additive manufacturing. So now I would like to I request Professor CP Paul sir to take over the presentation.
Hi, good afternoon, participant. It's my privilege to continue the talk, and specifically, I'll be talking on the AM and Industry 4.0. See, if we talk of the Industrial Revolution, and we will know that the first Industrial Revolution we had in the 18th century when steam engine was, invented. So what happened is at the time we converted the steam power into mechanical power, and we use extensively to build and make the many machines over there. And second revolution came when there was invention of the electricity, and the invention of the electricity changed the prime mover. The prime mover, which was a steam engine, was now electrical motors, and it brought a big changes to the scenario. Many things came on that time. But if you see, the basic cause of the second revolution was the invention of the electricity. Now, if you go to the third industrial revolution, the basic cause of the third industrial revolution was the discovery of semiconductor material. So, what happened the moment we got a semiconductor material? We started making different electronic devices. We started working on the PLCs. We started working on the robots. We talk of the programming. So many things came, and that brought a third industrial revolution into place. Now, we are entering into the fourth industrial revolution. And if you talk of the buzzword, for the fourth industrial revolution, it is cyber physical systems. Cyber physical system means you have a whole world integrated in a one net, and everything is being transformed one place to another. So this is the cyber physical systems. There is a fusion of real world and the virtual world, that is in the technology front. And also, if you talk of the business point of view, this is the time when the business decisions are being taken not only on the basis of the technical merits, but also they are seeing how the data are there, how can you decide and optimize the business strategies. So this is a big change into the scenario. And what I'm saying today, whole game plan is being seen as an integrated approach. Let it be the business strategies, let it be technology strategies, or let it be the digital world, or let it be the real world. So this is all what we are talking of. Bringing we are talking about fourth industrial revolution. See, there are nine. Uh, so what happened is this particular concept of industrial revolution was proposed in Hanover Fair in 2011, and as I already told, the basic driver for having this particular stuff was to availability of internet and internet of the things. So this what it is. It started integrating the technical process with the business volumes. Then digital mapping started coming in, visualization of the real world through the digital format, merger of physical and virtual world started going, and people started seeing holistically in one way. So what happened is his whole focus was on interconnectivity, automation, machine learning, and real-time data. So these are the basic stuff which is driving the things for the additive manufacturing. But if you see the whole industry 4.0, there are nine basic elements. You start from horizontal and vertical information flow, because what is happening, you think of a big company like Tata Motors or Tata Group. So they have got many companies working with, like for the Tata Motors are there, Tata Telco is there, Tata Steels are there. So many verticals they are working on it, and there is a very good amount of the flow of the information vertically, from shop floor to the top management, the information goes. But when it talks of doing it, sending the information across the horizontal, when I'm talking of transmitting the information horizontally, means whether telco and Tata Steel are sharing some information. And this is the problem. What is happening, since they are not able to share the information, many of the technologies there's such a big groups are doing, they are doing independently and doing the same mistake, repeating the same mistake at every front. Now, if these information can be shared, the things can be brought into the better. Therefore, this is the point we are talking of horizontal and vertical integration. Now, when we talk of the another point called simulations, simulation means not only the simulation of the process, not only the simulation of the design, not only the simulation of the thing, but here we're talking of from inception, the moment you conceptualize the product, to going to the dispatch of the company, the moment the material, the machine is thrown, so whole part is considered as an integrated way in the simulation. Now, still we have lot of challenges to achieve this simulation part, but again, this is the one of the primary pillar of the industry 4.0. The fourth part is autonomous augmented reality. Augmented reality means you have something real and something virtual, both have joined together. You are feeling that it is there, but really it is not. So that is bringing a lot of changes, and this is again the one of the pillar for the industry 4.0. And since we are talking of internet of things, we are talking of the large data sets, because you suppose you have a information gathered from station 1 and station 2, whole informations are being sent together, a lot of information is there, therefore you need to have a control on these data, and how to play with this data is a challenge. So that is the again making the things into different aspect. So what I want to say is that there are nine primary pillars in which whole industry 4.0 is handling, and one among them is industrial additive manufacturing. This additive manufacturing is basically making the things different. It is also interjacketing with the other pillars and making the whole process very attractive, very challenging. Now, if you see how the things will be, for example, you have a industry here. which is presenting the stuff, and we are trying to go well. So industry is having so many pieces and working together, physical part. And what is expected in industry 4.0, they have so many sensors inserted into it, informations are sent, and we have a virtual system. And this real sensor and virtual sensor are real system and virtual systems are integrated together, and all the information they are working, and we are able to see from there. I can give you a very good example. For example, you see a case. Suppose a aircraft flies from New York City to Delhi, and in this you have maybe 230 passengers sitting at. Now, if as far as the Industry 4.0 is concerned, they want to have an integrated digital twin concept in which what they want to have all the information about the cabin, engine parts, everything is taken from the aircraft and sent to the satellite. And from the satellite, the information is collected into one server. And what can we do? People do is they can real time cut the digital model of that, see the situation, what is being done in the aircraft. That sort of thing is possible with the. Therefore, things are making and becoming very different from what everything. So let me go to the poll, right? The poll is about the concrete printing, just which we studied a few minutes back. So you tell me, concrete printing follows which philosophy? Does it follow a material extrusion philosophy? Does it follow directed energy deposition philosophy? Does it follow material jetting philosophy, or none of this? So please vote for this. We are having a poll now. Yeah. So I'll say that the real answer is, the majority is on the right side. It is material jetting, because what are you doing? You have a motor for, and then you are, taking the jet, and pushing over it and depositing. So that sort of thing happens into this. Then we'll go for very quick next poll. Um, yeah. This is the result fantastic. So let me come to the point where we'll be talking what my lab is doing at RRCat. See what is happening so far. We heard what is in the textbook. We heard what is the world doing, and it is important for us to know what are we doing at RRCat in India. RRCat is an institute under Department of Atomic Energy, Government of India, and we are doing a lot of research in the area of additive manufacturing, especially laser additive manufacturing and metal additive manufacturing part. So let me tell you one thing: we have developed these two machines indigenously. One is called laser directed energy deposition machine, another is laser powder bed fusion machine. So these two machines are built. The machine that you are seeing on the left side, that is laser directed energy deposition, its cost is somewhere about 5 to 7.5 crores if you buy from a commercial market. But what we did is we developed these machines, and we are trying to push this machine into the Indian market in the price range of maybe somewhere about 1.5 to 2 crores. So that much advantage we can have. Another machine that you are seeing on your right hand side of the screen, that is laser powder bed fusion machine. This machine is typically cost common in commercial market from 3.5 crores to 5 crores. We developed these machines, and we are going to launch this in the range of 70 lakhs to somewhere about 1.5 crores. So that is the thing we are talking. So what I'm saying, since these technologies are developed at RRCat, very soon these machines will be in the market with the almost a price one third of the commercial price what we are getting this. So before pushing this to the commercial market, we also did a lot of research for various components. For example, one of the very typical component we developed for IG car using laser additive manufacturing machine. So this particular component that you are seeing is a very simple bushes. These are special bushes which are made up of Delaro 50 material. Delaro 50 is a nickel-based alloy, very hard material. If you talk of the hardness scale, the hardness scale comes out in the range of 800 to 850 VHN. So what people were doing earlier, they were making the substrate like this, and after that they were depositing using gas tungsten arc welding, Delaro 50 material, and they used to machine in and out for this to get these bushes. And these bushes are not possible using conventional this is not possible by using conventional manufacturing method. So this is the thing that we did, and after that we did the machining part of it, and we found that the fabrication time that used to take 45 days is reduced to 72 hours. Means, that sort of magic could be done, and we can have things can be done in bigger and bigger and better way. Another point I'm telling is that we worked on, how a porous material can be built, because we had been taught that porosity is bad. Porosity is bad in any material, but reality is the porosity is not bad. We are saying it bad because we do not have a control on the porosity, and since we do not have control on the porosity, we say it's bad. But again, if you have a control, if you are making an additive manufacturing, you see such a beautiful porous material is built, and you can see that graded porosity is achieved. Another very good example is of making a low cost tools. Suppose you are using a large diameter tool, like 50 diameter or 100 diameter, and if you want to use some we use sintered carbide tips to provide a cost effectiveness. But we are not doing this for low diameter tool, because it's not possible to tie that sort of thing, to inserts into that. So that is a major limitation. But we just thought, why don't we make a blank of low cost material and deposit tungsten carbide at the edge of maybe 3 millimeter or 5 millimeter diameter tools, and try to see the performance of that. So in that way, we could make a low cost tool, because shank, which is the major part of this, and it's not normally in solid carbide tools, we are using that as a very costly material. But in this, we don't need. So that sort of advantage we could derive. We made many components, many geometries. You see such a beautiful impaler. The diameter is about 75 millimeter, and then you see the dimension accuracy. We try to make a prototype lipid parts. We also made honeycomb geometry orifices. These are specific item for a nuclear reactor. One of the very good job that we did is making a titanium stainless steel graded transition joint. So this was the thing that we did. So what is happening? Titanium and SS, these two are not friendly materials. They are not. Um, that is not things will be going on. So that sort of thing is going on, right? So what we have to do is, what we did, since they are not friendly material, we joined them using friendly material, using some buffer material, that sort of thing done. A lot of stuff is going. Sorry, I'll just continue for a 2-3 minutes more, and after that we'll be stopping it here. Only a couple of slides are left, and you will love what India is doing in the area of the metal additive manufacturing. We made compact heat exchangers. You see printed circuit heat exchanger. You can think of a heat exchanger of the channel 1.5 to 2 millimeter small and almost 250 millimeter diameter. Can you think of making a 2 millimeter hole across? Or can you have a different channels? So that sort of things are done, and these things are basically required for the fourth generation of the nuclear reactor that is likely to come to the country. So that sort of things are being done with us. Now, when we talk of so much great, that's we are having a lot of informations. So we also discuss about what are the limitations of the technology. One of the limitations that we have, the high cost. See, now patents are expiring. What we want, we have done some efforts to bring up the machines, but more innovation is required to take it to the common man in the India. We have to really start working on the inverse relations between speed and accuracies. We have to work it out, found how the things can be done, and make the things in better and better way. We also have to take off the how quality assurance procedure can be done. These are the limitation today. For example, you go to make some high engine parts, then you need to a lot of qualification. But again, these things will be coming slowly, and people will be trying on this. But these are the limitation, and people are working on it. And I'm saying a lot of there is a unavailability of trained manpower to take up of such assignment. So if the people are learning and training, the things can be done, thing can be brought to a better and better way. So these are the challenges today we have shortage of qualified materials. We have speed and productivity in additive manufacturing. Repeatability, quality assurance are the issues. Industries standards are not there. Security is the issue. A lot of things are there. But what is happening? What we have to do as a people who are doing the research or who wants to join this mission to make this technology more popular, and to like something like we have laptop at our home, you can have a 3D printer doing a lot of job, that sort of thing can be done. So what happened, the area which you need to be work on is the machine and software development. People have to work on the development of the process. People have to work on the development of the material. We have to come up with the rules of the design rules so that things can be done better and better. We have to work on the characterization testing. And the most important part that we have to take up is to come for the education and training of this technology, so this technology can be brought to a level where things can be made in a bigger way. So what I want to summarize here, additive manufacturing is a joining of material to make parts directly from 3D models following layer by layer approach. There are many advantages, but you know what I'm saying, these advantages are has to be taken to the next level by customizing them, bringing them, adopting them, and doing the things in such a way that thing can be more close to our life, right? We already know that there are seven categories defined by the HTM. It is very attractive in case of aerospace, defense, biomedical, and other sectors. Industry 4.0 is coming and joining many of the things and very great. And there are challenges and opportunities. Whenever we are talking of the challenges, I always says we have opportunities and we have to work on things are to be done in better and better way. So what I say is things are doing good and great. Therefore, to have a very good manpower in the country, to have a feel of the technology, what is happening here, we are saying that we are bringing in this book. The book covers very good stuff. It is with the with as per is conforming to ASIT syllabus and many syllabus that is being followed in the country. So there is no need to have Indian writing style is Indian, which is more specific. We have many things into this. So I request you guys go through this book and let us know if there is any more things to be included into this as a feedback. With this, I stop my presentation for the day. For any other thing, thank you very much. If you have any other stuff, please do call to us for any support, anything. We are open for the any questions if you have. One question, it was in between, probably Junub can answer on to this. It was one of the guy was asking to repeat the uh, uh, process of laminated object manufacturing. Loan.
Okay. So laminated object manufacturing is not a standardized ASTM name, and it is sheet lamination is the process. And we have is the different sheet materials. Like if you have different sheet of materials or different thickness can be laid one over the other, and we join it and to make a component. So how we join the sheets is mainly by using adhesives or by using solid state welding techniques. If it is a metal based sheet, then we use solid state welding techniques, or if it is a paper or anything like that, we use adhesives. And we cut the shape of the sheet by using CNC milling generally. And we can say that sheet lamination is similar to a hybrid approach, and where we have addition of material as well as removal of material to get the shape out of it.
Another question that I was having is how can somebody join RRCAT? There are a couple of ways you can join. Number one, the basic recruitment to RRCAT comes from BRC online exam. You can write and join that. You can join as a trainee scientific officer, which can eventually into the scientist in this. Another part is you can also join, if you're a PhD guy, you can join through KSKRA fellowship, which is available from Department of Atomic Energy that you can do. Other aspect, if you want to have a boost in your career, you can join RRCAT's PhD program, which is affiliated to Homi Bhabha National Institute (HBNI). You can join that, like Jinup joined in 2016, and amazing work by Jinup. He published on more than 20 journal papers in last 5 years with 20 book, maybe with 4 book chapters and somewhere about 25 conference paper. So such a thing can be done because we have very good resources. People are working on in very focused way, and the book that you are going to see is also the part of this. So what I say is, ki, as far as the we are concerned at the Department of Atomic Energy and at RRCAT, we may not able to bring a big change into the stuff. We can only push the technology. We can bring the ideas, but if you want to make it a mass mission, so many people have to join. I'll take this opportunity to invite various universities and engineering institutes guys. They can write to us and contact us, and we can have a collaborative program with them so that a better technology can be brought out. It's not only the book, but in reality. So that is our mission. With that, I stop. If you have any other questions, I'll be happy to take up. One question was that in our presentation we have showed that RRCAT has developed the machine. We have developed this machine. These machines are likely to be available commercially within 2 years. We are in the process of pushing this and developing this through incubation. So that will take some time. To join the PhD, we you go to our website rrcat.gov.in. In that website, informations are available. Because this is there would be a section called opportunities. In opportunities, there would be a PhD program. You can click it. This year, we are not taking in the month of January. Again, we'll have a session where we will be taking the people to join the program with us. So that will be there. So this is where you can join PhD program, Rajkumar. Yeah. If there is any other question, please. Ujjwal, you were talking of staircase effect. I'll say that effect can be fixed in DD by maneuvering the head appropriately. That is one part. Second thing is in some other process, you have to go for the lower thickness in general so that staircase effect can be brought down. So that is very standard procedures, and this is really a very common question come into the mind of the people. And thank you very much, Ujjwal, for asking this question. When we talk of the difference between VAM and GMAW, I will take this question. Tapas. The difference is in gas metal arc welding, we are not starting the process from 3D model. It is not an additive manufacturing process. Whenever to cut off gas metal arc welding, it is a conventional method of making some components for welding. But when you are integrating this process with a 3D model, generating data, slicing, and whole bunch of your process that is required for a 3D printing to be, so then it is or additive manufacturing to be called, then it becomes a VAM. So that is the another answer to the question. My contact number, I'll be writing this on my chat box here. Let me see some other questions if there are. Yeah. So I'll be typing. I'm typing my mail ID is paulcp at rrcat.gov.in. So this is my email ID. You can write to me on this, and then we can have chat. And one of the simplest way to find me, just type Google, just Google CP Paul, CP Paul. Google it. So this will give you know about me and many things about us. So first six hit is ours. When we talk of Rinningham, future scope of adaptive machine learning process in additive manufacturing, lot of things are being done. See what is happening. Additive manufacturing is very good to start with. Lot of things are being done, but still it is fusing with other pillars. I told you already we have 9 pillars, so they are fusing in this. So machine learning process is basically, people are trying to use it for closed loop control, prediction of the some errors, and so many stuff. And we are also trying to work on these in these areas to make machine more smart. So that is the way. Arinandam, very nice question. Definitely we have take up. There is one question by Tapas. Yeah, I have done BTech and MTech from Mechanical Engineering Department. If I get an opportunity to PhD from Metallurgy and Medicine Department in any of the ITs, there will be any problem during my academic career to join as a faculty. I have to shift my department mechanical to metallurgical area laser based. Yeah. See, Tapas, it doesn't work this way. The way you are saying it doesn't work this way. For example, what is important is what you bring to the institute. Whenever they look for a somebody who is joining to them, they say what you have for them. See, the degrees are the requirement. For example, PhD is one of the prerequisites to be the faculty. But if you have a knowledge, if you have a expertise, and you bring to that institute, and there is a value addition to that, so that makes the thing different. And in most of the IITs, there is always a cross-discipline appointments, and many universities has got this concept. So what I'm saying, what you are good at, try to understand, try to work on it, and that will make your life much simpler and easier to move it, in spite of going back to mechanical engineering and thinking on that. So you need not to worry about this. What you are good at, please do it. Make your expertise visible, and your bring that expertise with you to the organization that you are joining. So that will make the things very much different. That's what. Yeah. If any collaboration, please do draw call to me. There was a word from Dr. Rajesh Sharma. He wrote to me. Yeah, fine. We are happy to collaborate and define the framework. I have Mr. Robinson Fernandez also, one of my former boss when I was working with the GE. So thank you, sir, for being part of the session. Microwave healing, yes, is the post processing. People are doing it. Dr. Satnam Singh, people are working on this area. This is also again coming up field. Some part of it we have covered in our book as a post processing part, but we have to do work on these things. So this is the status of the thing in India, and a lot of things we are doing. I do not see any other question. Comparison of
One question from
traditional and
Abdul.
additive manufacturing. Yeah.
One question from Abdul Bahab Hashmi. Can we use the same setup of SLM for purpose of post-processing operation like laser polishing? Yes, it can be used. The same setup can be
Yes, we
used for
can.
the
Yes, we can.
laser polishing.
Yes, it can be. It can be without any problem. It can be done. Only thing is, what I'm saying. Being the research for so many years, we are working on this, and a lot of things we are trying to do in this way. So yes, SLM setup can be used for post processing, but you have to play with smartly. How to manage and how to tame the machine is also a part of learning. So what I'm saying, when you have indigenous technology, we are not buying as a black box, and what we are getting in this particular book and stuff whatever is not the black box. What we learned in last 23 and 24 years, that is summarized here. Any other questions? Yeah. What I want to say is that we are also organizing one workshop on 3D printing of medical devices at NIT Calicut with Professor Jose. You guys, for those who are working in the area of additive manufacturing, please uh, join and try to be the part of this. Somehow, this is really very good stuff to work on and make the things happening in a big way. So this is opportunity where you can interact with many other experts in the country, specifically those who are working. A big pool of the experts are joining together for item manufacturing, which is likely to held on 17th and 18th of July at NIT Calicut. So I'll also be there. You can just see me there. Thank you. So that's all. If I don't see any other questions, most of the questions we have answered. Kali Charan Rath has written, kindly suggest few projects for funding proposal. Probably these things cannot be discussed. Please do write to me in person. We can have a discussion on those points, and we can take up the things into the next level. So if there is no question, I will stop here. Thank you very much for joining us. It was a pleasure. Now I'll just send um, uh, the organizers to please take up for the poll, final poll.